So for these next few problems, we're going to introduce a new tool for us to work with. Springs! Springs are a whole lot of fun, and we can use them to make all sorts of fun things like trampolines and spring scales. We can even use them to protect people if elevator cables snap. And springs add all sorts of fun problems to physics, so we're going to do a few of those now. But first, I just want to introduce a few of the concepts we're going to need to understand how springs behave. To make sure we're all on the same page for our discussion of springs, I want to go over some of the assumptions we make when we're talking about springs. We're going to assume that we can either compress springs, like this, or stretch them, like this. What we're not going to deal with is springs being pulled at an angle, like this. Now, you can actually handle problems like this in physics, but that's a bit beyond the scope of this class. So we're going to assume that the spring only moves in one dimension. It can either be squished or it can be pulled on to extend it. We're also going to assume that the mass of our springs is 0, so they're massless springs. Now that doesn't seem very realistic, but it's a really helpful assumption for solving our problems. And it turns out that in many cases, the mass of the spring is pretty small compared to the masses of the other things we're dealing with in the problem. So this assumption isn't a terrible one, but just know that if you were doing super realistic problems, we couldn't say that springs are massless. One important concept we'll need in our discussion of springs is this idea of equilibrium length. And to see what this is, let's look at a few examples. So first, imagine that we have a spring here that no forces are acting on. Nobody's pulling it or pushing it or anything like that. Even though it's not being pushed or pulled, it has some natural length that it likes to be at. It might be maybe 1/10 of a meter or something like that. We call this natural length of the spring the equilibrium length. Now if we pull on the spring or push on the spring to compress it or extend it, then we're going to change the length of the spring away from the equilibrium length. And the amount that the length of the string changes, we call delta x. So delta x is the change in the length of the spring away from the equilibrium length. It's important to note that both extending the spring and compressing the spring can change the length of the spring away from the equilibrium length. All right, now we're ready to talk about energy. If you push a block against a spring, you'll notice that you have to fight to keep it in that same spot. It wants to bounce back in the other direction. Similarly, if I try and pull on a block, extending the spring, it tries to pull back in the other direction. Now, if I let the block go, in either the case where I'm compressing the spring or in the case where I've extended the spring, the block's going to accelerate and go bouncing back and forth, which means that it's gaining kinetic energy. And if the block's gained kinetic energy, then energy must have come from somewhere. And it turns out that that energy was potential energy stored in the spring. And you'll notice that the more I stretch the spring, the more dramatically the block will rebound. In other words, it'll have more kinetic energy if I stretch the spring further or compress it further. So this means that the energy stored in the spring, the potential energy, should probably scale with the distance away from the equilibrium length. And in fact, it does. It turns out that we can write the potential energy stored in a spring as 1/2 times some constant k times delta x squared. And remember that delta x is the difference between the spring's current length and its equilibrium length. Now this constant k is something that's particular to the spring itself. It's a measure of how stretchy or stiff the spring is. Now you may be wondering where this equation came from. I'm afraid I'm not actually going to derive it for you because that requires calculus, but I will say that it's not a mathematical coincidence that this equation looks a lot like the equation for kinetic energy. That's a topic we can discuss more on the forums. All right, now I think we're ready to do a few problems using springs.